Okay, guys, so there's a few little things in this chapter I just want to clear up. We've gone through most of the code now. I want to talk about a little bit more about ensemble classifiers because we kind of hid that a little bit. We did a type of boosting and we also did some tree methods, but they were kind of wrapped in my kind of cross-validation code. So I just want to talk a little bit about how we combine classifiers. So first, let's just define this technique called bagging. So we have a classifier and we're going to make some sort of prediction with a classifier, and we'll call this prediction we'll give it the f function. We'll call it f star, and it's going to take in some information, my independent variables x. And what we're doing with bagging is we just create some overall bagged classifier. And imagine that we had B of these little classifiers, then basically we'll say for classifier B, we just aggregate the predictions. So imagine if our class is 1 or 0, we just kind of 1, 1, 1, 0, 1, 1, 1, 1, 0, 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Our average is 0.8. So our prediction is kind of closest to 1. Very easy. Now, imagine that we just had a single technique. So we just had a single technique. And it's a technique that like always gives the same results. So something like, k nearest neighbors. How do we make lots of classifiers? Well, the idea is we would make a training data set for each classifier. And for this, we'd use a technique called the bootstrap. And this is used a lot in statistics. And the key with a bootstrap is we sample with replacement. Now, what does that mean? Well, just the very simple example I gave in the notes. So imagine that you have, we would do sample without replacement. And you have like 1, 2, 3, 4, 5 different people here, or 5 different, the data set with 5 items. Now, if I'm sampling without replacement, say for example I randomly get 2 first, then we select 2. So we only, if we're not replacing, we have 1, 3, 4, and 5 left. So then we select 1. Then we select 3. Then we select 5, and then we select 4. So like this, if we want to select all 5 items, we only actually have 1 data set we could actually get. If we only had 2 items, there's lots of different data sets we could get. So that's not very good for us. But if we sample with replacement, each time we can select any of these 5 items, and we could select, so we have like a 0.2 chance of selecting each of these. And let's just say, okay, we select the 1, we select the 3, and each time we have a 0.2 chance of anything. So we could select the 1 again, we could select the 4, and then maybe we select the 3 again, or we could select the 2. So the idea is that we do this, and then we do it again, and we do it again, and each one we have a different data set, but is very similar and contains information from the original data set. So these are we'd have like B bootstrapped data sets. Now we look at the random forest. The random forest is interesting. The random forest can sometimes work a little bit differently. So what we have is we have a random forest, and we send it certain parameters. So we decide how many trees in the forest. And again, more trees in the forest, you get a richer kind of set of classification trees, but it takes much time. And then what we do is for each tree is we kind of set a subset of features. So we set for how many features for each tree. And then we say the minimum node size. This is, we talked when we did decision trees, we don't want to get our trees too large, otherwise they overfit. So each kind of, if we've got our tree here, and you remember maybe we had 50 items, we have 20 here, 10 here, 30, and we have 20 here. These guys should be greater or equal to the minimum node size. Okay, and so then what we would do is we'd actually create lots of trees, each with a different feature set, and we just say different randomly selected features. Until eventually we reach how many trees that we've decided, and then we kind of aggregate our predictions. Okay, and I wanted to do that because I know in the class people ask quite a bit about ensemble models, and there's some of this in the notes, so there will be a few questions on the exam. Okay, the second little thing I want to do, because again, it's going to be on the exam, is just talk a little bit about how we deal with text data. So we've converted text into sentiment. And what we did is and this was kind of hidden for us, so we had something called a sentiment lexicon. And, we'd match kind of words and phrases to kind of negative or positive or emotional sentiment. Now, what we want to think is when we're doing data mining with text is that text is pretty much useless to us. We can actually use the words as features. So let's just think we have a series of sports stories. And And our task is we want to kind of classify them as football or hockey. So we have a document. And we look for the word football. We have the word touchdown. And this is a really simple example. We have the word hockey. And we have the word puck. And you can see that some of the first two documents are a lot about football and have very little mentions of hockey. The third one probably mentions both. Sorry, this table's going to be a bit. And the fourth and the fifth are very strongly hockey. And we could actually use this in a lot of the algorithms we've done so far. So, I mean, we could actually do some cluster analysis with two clusters. We could do like a k-means. And we could kind of classify, you know, we could have two clusters. And in fact, if we had three clusters, these guys might be in one cluster. This one might be in one cluster with both, and this one might be in one cluster. Or even, you know, if we had a Y, and this said, yeah, this is a football story, this one's a football story, and this was a hockey, this was a hockey, and this was a hockey. So we have one in football, zero hockey. We could actually do some logistic regression. We could do some class classification. So this is, we have our documents and we have our term up here. So basically, to create this, we go through several steps. We first, you know, we have our text. Then we're going to split it into words. And we've got the counts for each word. We then will look for things like stop words. So we have what's called stop word maneuver. And this will remove kind of really common words. So if we have, for example, I'm a Chicago Bears fan, so I kind of lose track of all the quarterbacks because there's so many. Nick Foles scored you know, amazing touchdown. You can see an, this would actually be a stop word. Another thing we could do is what we call stemming. And that's we can have very similar words with kind of different endings, but they all kind of relate to the same word. So for example, I can code in R. I could have done some coding in R. I could have coded a great algorithm. All of these have the same stem, and so we just merge them into one word, like code or code. So this would now be a single word. And then we have the words and the counts. We've merged any similar stemmed words. We've removed anything not useful. And we have what we call, you know, we just have, like I showed before, we'd have our documents. And these are the items we predict, or, you know, we can predict things on, or we can classify. And these are the terms. Now what we could do is we could combine sets of 2 terms, and obviously be a lot of more of these. So it's like here a term would be touchdown, a second term, these are what's called 2 grams, could be something like amazing touchdown. Okay, so that's and then you could have 3 grams combinations of 3 words, but the point is as you have more and more different possible combinations of words, you get many, many more features. You could get, like, if you had like 1 grams, 2 grams, 3 grams, you're going to get hundreds of thousands of features. So you've got to stop somewhere. Quite often we will have the single document term, the 1 grams. And to give a little bit more context, we'd have the 2 grams. But generally, we wouldn't really go much further than that. And just to kind of end the chapter, I have a little example where I don't really do much classification here, but there's a library called TextMiner in R that can do a lot of this stuff. And it's got a function for creating the document term matrix. You give, this case, it's got the pizza requests. We actually have, you can set, here we have 1 grams and 2 grams. We can actually set some stop words. And what I've done is I've added 2 different inbuilt sets of stop words, one English stop words, another one that's called smart stop words, and I've added my own because this data was ripped from Reddit. There's some of these line feeds left in the data, so I want to get rid of those. So I do that manually. And again, we want everything in the same case. We remove punctuation, we remove numbers, and this just tells us how much output we give. Okay, and what we're doing now is we're actually going to create something called a word cloud. So firstly, what we're going to do, we're going to create something called probability words. And all that is that's just the column counts, the word counts or the bigram counts, divided by the total number of words in all the documents. So the sum DTM pizza is just the total number of words, and so it's just a measure of how common each of the words are. And we call this P. Now then what we do is we calculate it. What we're doing is we've got, for the different pizza results, i.e. I didn't have a pizza and did have a pizza, we're using the lapply function. We kind of go through the non-pizza, the people who are not awarded the pizza and the people who have a pizza, and we do the same measure. So we see how popular the word is with people who have not ordered a pizza and people who've had ordered a pizza, relative to how popular the word is in all the data. So we can say relatively, how much more popular a word is in our data set for pizza than by random in all of the data. And then what we do is we actually convert it into this word cloud. Yeah, and the word cloud, what it will do is we'll have basically the names of the words along with the relative frequency for the non-pizzas and also for the pizzas. And the best way to do a word cloud is just to show you what it looks like. And here we have, these are the people who weren't allowed a pizza. And you can see maybe they were too explicit in asking for pizza. They love pizzas and they're very hungry. Now, this is a bit weird. Why is Imager and HTTP Imager the most important thing? And I guess it's because people embedded an image. So maybe they embedded images of their starving families in order to get a pizza. But also things like pay forward, saying, hey, you give me a pizza and when I'm better off, I'll pay forward. Paycheck, I got the order being a paycheck. Forward as in pay forward as well. Work weeks, unemployed, recently, again, a slightly different version of pay forward. These are the things that will, and edit, I guess it's because people who edit their posts actually are more likely to get pizza and like more engaged. Okay, so that's it.